So every single time you pull out your phone, to open a map application and route your way to a new restaurant or, I don't know, a friend's house, you are actively relying on time travel.
Yeah, quite literally.
You are relying on the fact that these atomic clocks orbiting the Earth right now
Hmm.
they're experiencing time at a fundamentally different rate than the phone sitting right there in the palm of your hand.
Which is just wild to think about.
It is. And if the universe didn't work in this utterly bizarre, completely mind-bending way, the navigation system in your car would drift by about 10 kilometers every single day.
Right.
Like within a week, your digital map would basically think you were parked in the middle of the ocean.
It really is this profound reality check. I mean, we walk around completely oblivious to the fact that the fabric of reality is just warping and flexing around us constantly.
Yeah.
But we literally carry the confirmation of curved space and stretched time right in our pockets every day.
And that brings us to the core of this deep dive today. So you have almost certainly heard the famous slogan, probably thrown around at a dinner party or in a movie somewhere, that, Einstein proved everything is relative.
Ugh, yeah, that phrase.
Right. It sounds deeply philosophical. It makes for a great bumper sticker.
Yeah.
But as a summary of the actual science, it is completely hopelessly backwards.
It really is.
Because the truth we're going to explore today, drawn from this really fascinating stack of sources we've compiled, is that the theory of relativity is actually built on something being absolutely stubbornly, non-negotiably fixed.
Yeah, the word relativity itself is almost like a tragic piece of public relations for the theory.
Right, like a branding issue.
Exactly. It leaves people with this vague, kind of wishy-washy impression that reality is just whatever your perspective happens to be. Like, there are no hard rules at all.
But really, it's the exact opposite.
It is the exact opposite. The physics we are diving into today are about an ironclad dictatorship of the universe. I mean, every single weird consequence we're going to talk about, from shrinking spaceships to clocks running slow, it all happens specifically because the universe completely refuses to compromise on one single unbreakable rule.
Which is just so cool.
Yeah.
So our mission today is to completely reshape how you understand your place in the universe. And for those of you listening who might feel a bit intimidated by physics, let me assure you right now, we are leaving the dense textbook math at the door.
Oh, absolutely. No pop quizzes here.
Right. You're going to unpack exactly how insisting on this one fixed rule broke our everyday common sense understanding of time and space.
Yeah.
And we're going to do it step by step. But to understand what Albert Einstein broke in the early 1900s, we have to start with the foundation he was standing on.
Yeah, we have to go back centuries before him.
Exactly. To this perfectly logical, universally accepted rule from the 1600s.
So we need to talk about Galileo, because Galileo actually gave us the original principle of relativity. And to really wrap our heads around his idea, we just need to define one pretty straightforward concept, which is constant velocity.
Okay, let's break that down.
So for our purposes today, moving at a constant velocity just means moving smoothly, straight ahead. You are not hitting the gas pedal to speed up, you're not slamming on the brakes to slow down, and you are not turning the steering wheel.
Just a smooth, continuous, completely unchanging glide.
Exactly. And the classic thought experiment here, which I know you love, involves putting you inside a sealed cabin below the deck of a really massive ship.
Oh, I do love this one. So imagine this ship is moving perfectly smoothly across the ocean at a constant speed. You are down there in this little cabin. There are no portholes to look out of. You can't hear the water, can't feel the wind.
You are completely isolated from the outside.
And Galileo's brilliant insight was pointing out that there is absolutely no physical experiment you can perform inside that sealed room to figure out whether the ship is actually moving through the water or whether it is just sitting perfectly still, tied up at the dock.
Right. I mean, if you hold a rock out in front of you and just drop it, it falls perfectly straight down to the floorboards.
Doesn't curve backward toward the rear of the ship just because the ship is moving forward.
Exactly. And let's upgrade that to an experience you listening to this have probably had recently. Think about the last time you were on a commercial airplane.
Yes, perfect analogy.
You're cruising at 35,000 feet, doing like 500 miles an hour. If the air is perfectly calm, no turbulence at all, and you have the window shade pulled down, your body has zero physical sensation of that immense speed.
None at all.
If you pour a glass of water, the water pours straight down from the bottle into the plastic cup. It doesn't, splash backwards onto the poor person sitting in the row behind you.
Thank goodness.
Right. Inside that cabin, the water, the cup, and your own body all behave exactly as if you were sitting perfectly still at your kitchen table back on the ground.
So let's take that mundane observation and really follow it all the way to the bottom. Like, what does that imply about the fundamental nature of the universe?
It implies something huge. It implies that the laws of physics are completely identical for anyone moving at a constant velocity.
Right.
There is no special privileged state of being absolutely at rest. Like all constant motions are equally valid frames of reference.
Which is pretty humbling when you think about your own physical state right now. I mean, you might be sitting on your couch listening to this feeling utterly stationary, but you are on a rocky planet hurtling around a star at roughly 30 kilometers every single second.
Yeah, it's wild. And that star, our sun, is orbiting the center of the Milky Way galaxy at over 200 kilometers a second.
But your coffee stays perfectly still in your mug.
Exactly. Galileo's principle means the perspective of the person standing on the dock, the person sailing on the ship, and the person flying on the airplane are all equally true. None of them can claim to be the one who is, like, truly standing still.
And our intuition handles that beautifully. It makes perfect logical sense. And the scientific community was totally happy with that uncontroversial idea for centuries.
They really were.
But then the 1860s roll around, and a Scottish physicist named James Clerk Maxwell essentially throws a grenade into the room.
He really did. Maxwell is one of those monumental figures whose work just underpins the entire modern world. In the 1860s, he accomplished something staggering. He mathematically unified electricity and magnetism.
And just huge.
Yeah, he wrote down this set of equations that described exactly how electric and magnetic fields behave and interact. But when he pushed the math to its logical conclusion, he stumbled onto a prediction that literally no one saw coming.
Right. The math predicted the existence of waves.
That's the grenade.
Yeah.
His equations show that if you wiggle an electrical charge, it creates a ripple in the electromagnetic field, and that ripple travels outward through space as a wave.
Okay.
Furthermore, Maxwell's math didn't just say these waves existed. The equations actually spit out the specific mandatory speed at which these electromagnetic waves must travel.
And here's the light bulb moment, literally. Because when Maxwell looked at the speed his math demanded for these invisible electromagnetic waves, it perfectly matched the known measured speed of light.
Yes.
Boom! Light itself is an electromagnetic wave. That feels like a massive triumph. I mean, science figured out what light actually is.
It was a huge triumph. I mean, it ranks right up there with discovering DNA. But it instantly triggered a catastrophic logical problem for the world of physics.
Right. Because Maxwell's equations didn't say the speed of light is 300,000 kilometers per second, give or take. It gave a hard, specific number.
Exactly.
And whenever you talk about speed, you always have to answer the question, speed relative to what?
And to understand the panic this caused, we have to look at how physicists in the 1800s understood waves. To them, a wave wasn't a physical object. A wave was a disturbance traveling through physical medium.
Okay, like what?
Well, think about sound. Sound is a wave of pressure traveling through the air. If you are in a vacuum chamber with no air, there is no sound because there is literally nothing to carry the wave.
Right. Or a ripple in a pond is a wave traveling through water.
Exactly. The speed of a wave is always measured relative to the medium it is traveling through.
So the logic trap kind of snaps shut here. If light is a wave, the scientists of the 1800s thought there absolutely must be some sort of invisible ocean everywhere in the universe for the light to wave through. You can't have a wave without water, so to speak.
That was their assumption. They called this hypothetical medium the luminiferous ether. They assumed it was this frictionless, completely transparent substance that just filled the entire vacuum of space.
Okay.
And if this ether exists and the Earth is orbiting the sun at 30 kilometers a second, then the Earth must be plowing through this ether ocean, creating an ether wind.
So let's use the swimmer analogy to really visualize what they were trying to test here.
Good idea.
Imagine you are standing on the bank of a river and you're watching a swimmer. If the swimmer dives in and swims downstream, moving with the water's current, you are going to measure them moving very fast relative to you on the riverbank. The river is helping them along.
Right, they get a boost.
But if they turn around and swim upstream, fighting against that current, their progress relative to you on the riverbank is going to be much slower.
And that is exactly how they conceptualized light moving through the ether. If you shine a beam of light in the same direction the Earth is plowing through the ether, the light should get a little speed boost from the current.
Right.
If you shine it in the opposite direction, fighting the ether wind, it should measure a tiny bit slower.
which sets the stage for one of the most famous failures in scientific
Oh,
history.
absolutely.
So, in 1887, two American scientists, Albert Michelson and Edward Morley, decided they were going to measure this ether wind.
Hmm.
And they didn't just eyeball it. They built an exquisitely sensitive machine called an interferometer.
The engineering was just phenomenal, especially for the late 19th century. They essentially built a device that took a single beam of light, split it in half, and sent the two halves racing down two different tunnels set at right angles to each other.
Okay.
The light would hit mirrors at the ends of the tunnels, bounce back, and then recombine.
The idea being that one of those light beams would be swimming upstream against the ether wind, and the other would be swimming cross-stream. So they should take slightly different amounts of time to complete the round trip, right?
That was the expectation, yeah. And because light moves so fast, they knew the difference in time would be microscopic.
Very tiny.
To prevent any vibrations from ruining this delicate measurement, they mounted their massive sandstone block of mirrors on a pool of liquid mercury in the basement of a stone building.
Wow.
They isolated it from passing horse-drawn carriages, from temperature changes, from literally everything. They were absolutely ready to detect the absolute motion of the Earth through the invisible fabric of the universe.
So they run the experiment, they check the results, and nothing. A complete, undeniable null result.
Yep.
The two beams of light returned at the exact same split second. The light traveling upstream moved at the exact same speed as the light traveling cross-stream.
It was devastating for them. I mean, they rotated the heavy sandstone block on its mercury pool, pointing the arms in different directions. Null result.
Wow.
They waited 6 months until the Earth was on the opposite side of the sun, moving in the completely opposite direction through space. Null result. No matter which way the Earth was moving, no matter which way the light was pointed, the speed of light never changed by a single fraction of a millimeter per second.
Let's just sit with that panic for a second, because
Yeah.
it violates all basic logic. It is like watching a river swimmer move at exactly 5 miles an hour over the riverbank, regardless of whether they are floating lazily with a raging current or swimming frantically against it.
Yeah, it makes zero logical sense.
The scientific community completely scrambled, right?
Yeah.
They tried to invent all these convoluted mathematical patches, suggesting the ether was somehow dragging along with the Earth or like physically squishing the mirrors.
They spent nearly 2 decades twisting themselves into knots trying to save the ether theory. And then, in 1905, a 26-year-old patent clerk named Albert Einstein looked at this mess and made a move of just breathtaking audacity.
He really did.
He said, "Stop trying to fix the ether. The experiment isn't broken. Our core assumption about reality is broken." He took the bizarre result of the Michelson-Morley experiment and simply declared it a fundamental law of nature.
So he published a paper built on two basic postulates.
Ugh.
And, think of a postulate as a foundational, non-negotiable rule. If you accept the postulate, you have to accept everything that mathematically follows from it.
The exact same.
So what was the first rule?
Postulate 1 was just a reaffirmation of Galileo. The laws of physics are the same for all observers moving at a constant velocity. There is no absolute rest, and there is no ether acting as a universal background.
Okay, we are comfortable with that one, the smooth sailing ship. But rule number 2 is where the universe kind of breaks.
Yeah. Postulate 2, the speed of light in a vacuum is exactly the same for every observer, regardless of their own motion or the motion of the objects shining the light.
That sentence sounds so unassuming,
Yeah.
The speed of light is the same. But when you force your brain to actually visualize what that demands, it is terrifyingly weird.
It really is.
I want to try a thought experiment here to prove just how violently this clashes with human common sense. Imagine I am standing perfectly still on a dark road. I turn on a powerful flashlight. The beam of light shoots out of the bulb at the speed of light, roughly 300,000 kilometers per second.
Correct. That is the universal speed limit.
Now imagine you are in a futuristic, super fast car. You are driving straight toward me, and you are driving at exactly half the speed of light, 150,000 kilometers a second.
Okay, I'm moving fast.
My flashlight beam is rushing toward you, and you are riding toward it. Everything in my human experience tells me that your speed and the light's speed should add together. Like if a baseball is thrown at 50 miles an hour, and you drive your car toward the pitcher at 50 miles an hour, that ball is going to hit your windshield at 100 miles an hour.
Right, it's basic addition.
So, logically, you should measure that light beam slamming into your spaceship at 450,000 kilometers a second.
That is what human intuition just screams must happen. But Einstein's second postulate says nature doesn't care about your intuition. You will not measure the light approaching at 1.5 times the speed.
Oh,
No, You will pull out your radar gun, measure the beam rushing at you, and the readout will say exactly 300,000 kilometers per second, the exact same as if you were parked.
I really need to press on this. Are you telling me that my incredible speed rushing headlong into the beam does absolutely nothing to change the speed at which that light hits me?
Not a single decimal point. But let's make it even worse. Let's flip the direction. Imagine I shine the flashlight, and you are running away from the beam in your spaceship. You floor the accelerator until you are traveling at 99.9% of the speed of light. You are flying away from me at roughly 299,000 kilometers a second.
Okay, so the light is barely faster than I am? It should look like it's just creeping past my window, slowly pulling ahead?
No. When you measure the speed of that light beam passing you, it is not creeping. It is rocketing away from you at the full, unreduced speed of 300,000 kilometers per second.
Wait, really? Yes.
Yes, even though you are chasing it at 99.9% of light speed, it pulls away from you exactly as fast as it pulls away from me standing completely still.
This feels like a math error. Like speeds simply do not add and subtract the way they do in our everyday lives.
They absolutely do not. The speed of light is dictatorship. It does not matter how fast you are moving, and it does not matter how fast the source of the light is moving. Every observer, everywhere, always measures light moving at the exact same speed relative to themselves.
But something has to give. I mean, if I am standing still and measure the light moving at speed x, and you are rocketing through space and you also measure it at speed x, the mechanics of reality are breaking down. The equation cannot balance unless something else changes.
And this is the absolute genius of what Einstein realized. We have to look at the mathematical formula for speed. It is the first equation you learn in middle school. Physics speed equals distance divided by time.
It's a fraction. If you drive 100 miles in 2 hours, your speed is 50 miles per hour, distance over time.
Exactly. Now apply that fraction to light. If the final answer to that equation, the speed, is rigidly, non-negotiably locked at 300,000 kilometers per second for absolutely everyone, regardless of their motion, then the variables inside the fraction are the only things left that can change.
The numerator and the denominator.
Yeah.
The distance and the time.
If you and I are moving at wildly different speeds relative to each other, but we are both forced by the universe to arrive at the exact same final number for the speed of light, then we must disagree about how much distance the light covered, and we must disagree about how much time it took.
Wow.
In order to protect the fixed speed of light, space and time themselves must bend and stretch.
I want to walk through exactly how time stretches because just being told time slows down sounds like magic. There is a classic visualization for this called the light clock thought experiment, and I think we need to build it right now for the listener.
It is definitely the best way to demystify the mechanism. So let's build a highly simplified clock. Instead of gears and a pendulum, imagine a tall glass tube. At the bottom of the tube is a mirror, and at the top is another mirror.
Got it.
We trap a single particle of light, a photon, inside. It just bounces straight up, hits the top mirror, bounces straight down, hits the bottom mirror, up, down, up, down. Let's say one round trip equals one tick of our clock.
Perfect. Up is tick, down is talk. Very simple.
Now, take that glass light clock, put it inside a transparent train car, and send that train flying past you down the tracks at incredible speed. You are standing perfectly still on the station platform, just watching it zoom by.
Okay, I'm watching the train.
Inside the train car, there is a passenger standing right next to the clock. From their perspective, moving along with the train, what does the photon do? It just bounces straight up and straight down. Tick, tock. To them, the clock is completely normal.
Right.
But what do you see from the platform?
Well, as the photon leaves the bottom mirror and starts traveling upward, the train is moving forward down the track. So by the time the photon reaches the ceiling, the top mirror has moved forward.
Exactly.
So from my perspective, standing on the platform, the photon didn't travel straight up. It traveled on a diagonal slope to catch up with the moving mirror.
Precisely. And on its way back down, the bottom mirror continues to move forward, so the photon travels down on another diagonal line. From your perspective on the platform, the photon is tracing a zigzag pattern like a series of diagonal V-shapes.
And here is where the geometry really traps us. A diagonal line from the floor to the ceiling is physically longer than a straight vertical line.
It is a longer distance. The photon in the moving clock has to cover more ground to complete one tick than a photon in an identical clock sitting stationary on the platform next to you.
But wait, the dictatorship of light. The photon cannot speed up to cover that extra distance. It is locked at 300,000 kilometers per second.
That is the inescapable conclusion. The speed is fixed, the distance is longer. Therefore, the photon must take a longer amount of time to complete the trip.
Wow.
From your perspective on the platform, that moving clock literally takes longer to complete a single tick. Time for the moving clock has stretched out. It has slowed down.
Let me make sure I'm being absolutely clear for you listening to this. This isn't a mechanical defect of the clock. This isn't an optical illusion where it just looks weird because it's moving fast.
It is not a trick of the light, and it's not a delay in the signal reaching your eyes. Time itself, the actual progression of reality, is genuinely passing slower on that train relative to you on the platform.
That's just wild.
And remember Galileo's principle, the passenger on the train is equally valid in saying they're stationary and you are the one rushing backwards. So if they look out the window at a clock you are holding, they see your time passing slower.
Oh, man.
Time is not a universal ticking metronome in the background of reality. It is a local, personal experience intimately tied to how you are moving through space.
This phenomenon has a specific name in physics, right? Time dilation. Moving clocks run slow. But that was only the denominator of our speed fraction. What happens to the numerator? The distance.
The necessary counterpart to time dilation is length contraction. Just as time stretches, physical space compresses. If you measure an object that is moving rapidly past you, you will find that it is physically shorter along the direction of its motion than if it were sitting still.
So if a 100-foot spaceship flies past me at near light speed, and I take a high-tech snapshot of it to measure its length, it won't be 100 feet long. It might measure as 50 feet. It literally occupies less physical space in my universe.
And again, it's not an illusion. It is a genuine feature of the geometry of space. And this brings us to the third and perhaps most unsettling consequence of special relativity. It's called the relativity of simultaneity.
This is the one that really messes with the idea of a shared reality.
It does, because it deletes the concept of a universal now. If time and space are flexing and stretching differently for different observers based on how they are moving, then two events that happen at the exact same moment for one person will not happen at the same moment for someone else.
Let's stick with our train analogy to explain this. Say I am standing on the platform, exactly halfway between the front and the rear of the platform. Suddenly, two lightning bolts strike, one at the very front of the train platform, one at the very rear. The light from both strikes travels the exact same distance to my eyes, so I see them at the exact same moment. I say, those strikes were simultaneous.
But now consider the passenger on the super-fast train flying past you. Let's say they are exactly alongside you at the moment the lightning strikes. The light from the front strike and the rear strike begins rushing toward them.
Right?
But their train is moving rapidly toward the light coming from the front and away from the light coming from the rear. Because the speed of light is constant, the light from the front has less distance to travel to reach them, while the light from the rear has to catch up.
So the passenger sees the lightning hit the front of the train first, and a moment later they see the lightning hit the rear.
And here is the kicker. You are both perfectly mathematically correct. The strikes were simultaneous in your frame of reference. They were not simultaneous in theirs. You cannot agree on the chronology of events. Your now is not there now.
This is usually the point where someone listening asks the very reasonable question. If this is the fundamental nature of reality, if time stretches and objects shrink, why have I lived my entire life without ever noticing it? Why doesn't the highway look like a funhouse mirror when cars drive by?
It entirely comes down to the scale of speed. The speed of light is unimaginably fast compared to our daily lives. At everyday speeds, like a car on the highway, a commercial jet, even the International Space Station orbiting at 17,000 miles an hour, these relativistic effects are infinitesimally small.
Like, unnoticeable.
A car passing you on the highway is physically shrinking, and the driver's watch is ticking slower, but the difference is on the scale of fractions of a billionth of a percent.
Right.
Our brains evolved to hunt gazelles and gather berries on a slow-moving savanna. We never needed to develop an intuitive grasp of near-light speeds. The math shows that these extreme warpings of space and time only become dramatic and obvious as you accelerate to a significant fraction of the speed of light.
Okay, but playing devil's advocate here. If we can't see it with our eyes, and it only happens noticeably at speeds we've never achieved with humans, how do we know this isn't just a mathematical parlor trick? Like, how do we know Einstein didn't just invent a fantasy universe on a chalkboard?
Because we measure it constantly. The universe actually provides us with perfect little natural laboratories to prove it. The most beautiful example from the source material involves a tiny particle called a muon.
Oh, let's do a deep dive on muons, because this is where the abstract math hits the physical ground. what is a muon?
Muons are subatomic particles, somewhat similar to electrons but much heavier. And importantly, they are unstable. They are created continuously in the upper atmosphere, about 10 miles above our heads, when high-energy cosmic rays from deep space slam into gas molecules.
When you say unstable, you mean they don't last long. They decay.
They blink out of existence almost immediately. A muon has a well-measured average lifespan of about 2.2 microseconds. That is 2.2 millionths of a second.
That's nothing.
Exactly. Even traveling at nearly the speed of light, as they do when they are created, a simple Newtonian calculation shows they should only be able to travel about 600 meters before they decay and vanish.
So they are born 10 miles up, and they should die before they even travel half a mile.
Yeah.
Logically, none of them should ever reach the surface of the Earth.
Yet, if you set up a particle detector on the ground, you are bombarded by them. Huge numbers of muons survive the 10-mile journey. Without the flexible space and time of special relativity, this survival is physically impossible. It's a paradox.
But with Einstein, it works.
Yes. When we apply Einstein's rules, the mystery evaporates. Let's analyze the trip from both perspectives, starting with ours on the ground.
Okay, so from our perspective standing next to the detector, the muons are hurtling down through the atmosphere at 99% of the speed of light. Because they're moving so incredibly fast relative to us, time dilation kicks in. We observe the internal clock of the muon drastically slowing down.
Yes. From our point of view, time is barely creeping by for the muon. Because its clock is ticking so slowly, its 2.2 microsecond lifespan is stretched out immensely. It lives long enough to cross the 10 miles and hit our detector.
Okay, that explains how we see it. But what about the muon's perspective? Because we agreed earlier that the muon has every right to say, I am stationary and the Earth is rushing up to meet me at 99% of the speed of light.
Exactly.
But if the muon feels like its clock is ticking normally 2.2 microseconds, how does it think it survived a 10-mile trip?
This is where length contraction steps in to save the math. From the muon's stationary perspective, the Earth and its entire atmosphere are rushing toward it at near light speed. Therefore, the atmosphere physically contracts.
Oh, I see where this is going.
From the muon's point of view, the distance from the top of the atmosphere to the ground isn't 10 miles. It is violently squished down to just a few hundred meters.
Oh, wow. So from our view, the muon lives longer. From the muon's view, the journey is physically shorter.
And when you run the calculations for both frames of reference, the math yields the exact same physical result. The muon successfully impacts the detector. It is a stunning daily confirmation of relativity.
That's incredible.
And we don't just see this with cosmic rays. We do this ourselves. We have taken highly sensitive atomic clocks, synchronized them perfectly, left one on the ground, and flown the other around the world on a commercial jetliner.
This was the Hafeel-Keating experiment in the 1970s, right?
Exactly. When the aircraft landed, they put the two clocks side by side. The clock that had been moving at high speed on the airplane had recorded slightly less time. It was measurably out of step with the ground clock by the exact fraction of a second Einstein's formulas predicted.
Which means time travel is real. I mean, if you spend your life flying around the globe as an airline pilot, you are physically, technically, a tiny fraction of a second younger than you would have been if you chose a desk job.
Yeah.
You have traveled slightly into the future relative to the rest of us.
Which naturally leads us to the most famous puzzle in all of relativity, the twin paradox.
I am so glad we are tackling this, because the twin paradox is often presented as this fatal flaw that breaks the whole theory. Let's lay out the scenario.
Go for it.
We have two identical twins. Twin A gets into a high-tech spacecraft, fires the engines, and zooms off to a distant star system at 90% of the speed of light. Twin B stays home on Earth.
The traveler reaches the star, turns the ship around, and flies back to Earth at the same incredible speed. When they reunite, Twin A, the traveler, has only aged a few years, while Twin B, the stay-at-home sibling, is an old person. The traveler has leaped decades into the future.
Now, here comes the pushback. Here is the paradox. We spent the first 30 minutes of this deep dive establishing that constant motion is entirely relative. There is no absolute rest. So couldn't the twin in the spaceship say, I never moved, I just sat at my ship. It was the Earth that zoomed away from me at 90% light speed, and then the Earth came back.
Right, they could argue that.
If both perspectives are valid, shouldn't Twin A see Twin B's clock as running slow? Why does only one twin come back younger? Why isn't the aging symmetrical?
It is a brilliant question, and it's the exact trap the paradox sets. The resolution relies on a crucial detail that is easy to gloss over. The situation is not symmetrical. One twin did something the other didn't.
Which is what?
Acceleration. Twin B on Earth sat in one single constant inertial frame of reference the entire time. But Twin A, the traveler, did not. To leave Earth, they had to fire rockets and accelerate. To turn around at the distant star, they had to hit the brakes, violently decelerate, turn the ship, and accelerate back.
And acceleration, unlike constant velocity, is not relative.
Let's go back to our sealed cabin on the ship. If the ship is gliding at a constant speed, you can't feel it. But if the captain suddenly throws the engines into reverse or sharply yanks the wheel to the right, you are thrown against the bulkhead.
Yeah, you feel
You
that.
feel a physical force. You can close your eyes in a windowless room and still know absolutely that you are accelerating. Acceleration is a measurable, absolute change in your state of motion.
So because the traveling twin fired their engines and felt that crushing G-force when they turned around, their frame of reference shifted. They broke the symmetry.
Exactly. When you map this out on a mathematical diagram of spacetime, the twin who stays on Earth travels a straight line through time. The twin who accelerates takes a bent, indirect path.
Okay.
In the strange geometry of spacetime, the bent path taken by the accelerating twin actually results in less proper time experienced. The traveler's biological clock, their atoms, their thoughts, all of it physically ticked fewer times. It is not a paradox. It is a permanent asymmetry caused by acceleration.
It's beautiful, but resolving the twin paradox actually exposes a massive glaring gap in the theory Einstein published in 1905.
It exposes a massive limitation. Everything we have talked about so far, time dilation, length contraction, the flexible equations, falls under the umbrella of special relativity.
And it's called special because it only applies to a very special, highly restricted scenario constant velocity.
Yeah.
Straight lines, no speeding up, no slowing down.
Right, but look around the universe. Almost nothing moves in a perfectly straight line at a constant speed. Planets orbit in circles, stars explode, galaxies spin, apples fall from trees, accelerating as they drop.
The universe is defined by acceleration and gravity.
Exactly. And special relativity completely ignored gravity. It had no mechanism to explain it.
Einstein knew this, right? He knew his masterpiece was fundamentally incomplete.
He knew it immediately, and it tormented him. He spent the next 10 years in a state of exhausting, agonizing mental struggle, trying to fold gravity and acceleration into his flexible space-time.
10 years.
It required mathematics so complex, like non-Euclidean geometry, that he had to beg his mathematician friends for help. But in 1915, he finally emerged with what is widely considered the single most beautiful intellectual achievement in human history, the general theory of relativity.
General relativity. The rewrite of gravity. How did he bridge the gap between his rule for constant motion and the chaotic reality of acceleration?
He built the bridge with another brilliant thought experiment, an idea so profound that Einstein later described it as the happiest thought of his life. We call it the equivalence principle.
Here, going back into a sealed box for this one, are we?
Yes. Imagine you are standing inside a small, windowless elevator or a lift. You are standing there, your feet planted on the floor, and you feel your normal, everyday body weight pressing down.
Okay, I feel gravity pulling me down.
Einstein asks a devilish question. Are you sitting completely stationary in a building on Earth, feeling the pull of planetary gravity? Or are you actually floating in completely empty, gravity-free deep space, but a rocket engine is attached to the bottom of the elevator, pushing the floor up into your feet, accelerating you constantly at exactly 9.8 meters per second squared, the exact rate of Earth's gravity?
And my mind rebels at this, because the answer is, I can't know.
You can't.
If I take my keys out of my pocket and let go of them, what happens? If I'm on Earth, gravity pulls the keys down to the floor. If I'm in the accelerating rocket elevator in deep space, the keys just hover where I let go of them, but the floor of the elevator is rushing upward and smacks into the keys at the exact same speed. There's literally no experiment I can do inside that closed box to tell the difference.
The sensation of gravity and the sensation of mechanical acceleration are utterly identical. And to solidify this, we look at the inverse scenario.
Okay.
Imagine you are in that elevator and you are floating completely weightless. You let go of your keys and they just drift next to your shoulder. Are you drifting lazily in deep interstellar space, far from any mass? Or has the cable on your Earth elevator snapped and you are in free fall, plummeting down a shaft in total gravitational free fall?
Again, inside the box, it is completely indistinguishable. Because I'm falling and the box is falling at the exact same rate, I float. I feel zero gravity.
Einstein seized on this absolute indistinguishability and declared gravity and acceleration are not just similar. Locally, they're the exact same thing. And this equivalence completely destroyed Isaac Newton's centuries-old definition of gravity.
Because Newton taught us, and we still teach it in grade school, honestly, that gravity is a pulling force. The Earth throws an invisible lasso around the moon and pulls on it. The sun pulls on the Earth. It's a force acting across a distance.
But if gravity is identical to acceleration, Einstein realized it might not be a pulling force at all. He realized that the presence of massive objects like stars and planets actually warps the fundamental four-dimensional geometry of space and time.
Okay, this is the crux of general relativity, and it is notoriously hard to visualize. The classic analogy that everyone defaults to, and it is in the notes we gathered, is the rubber sheet analogy.
Yes, the trampoline with the bowling ball.
Right. You take a large, tightly stretched sheet of rubber. You place a heavy bowling ball in the very center. The weight of the ball causes the rubber sheet to sag, creating a deep, funnel-like dip. That bowling ball represents a massive star, like our sun.
Okay, I picture it.
Now, if you take a smaller marble, representing a planet like Earth, and you roll it sideways across the sheet, the marble doesn't travel in a straight line. The curved shape of the rubber forces the marble to travel in a circle, orbiting the bowling ball.
It is a ubiquitous analogy. You see it in every science documentary. But since we are doing a deep dive today, we need to critique this analogy because if you push on it even a little bit, it completely falls apart.
Really? Why? It seems like a great visual.
Think about the mechanics of the rubber sheet. Why does the bowling ball pull the rubber down to create the dip? Because the real gravity of the Earth is pulling it down.
Oh, right.
Why does the marble circle the funnel instead of flying off? Because real gravity is pulling it down the slope. The analogy uses gravity to explain gravity. It relies on a downward pull to explain how the solar system works. But out in the vacuum of space, there is no down pulling on the sun.
Oh, that's a glaring circular flaw. I actually never thought about that.
But there is a second, even more critical flaw. The rubber sheet only visualizes the bending of physical space. It completely ignores the bending of time.
Wait, the bending of time.
Yes, and here is a truth that surprises almost everyone. For slow-moving objects in our daily lives, like an apple falling from a branch or even the Earth slowly orbiting the sun, it is actually the curvature of time that is the dominant cause of what we feel as gravity.
Wait, I need you to slow down and explain that. How does the bending of time pull an apple off a tree?
It sounds like magic until you look at the mechanism. Remember from special relativity that time stretches differently depending on your perspective. General relativity adds a new rule: time ticks slower the deeper you are in a gravitational field. A clock on the surface of the Earth ticks microscopically slower than a clock floating in deep space.
Okay, so time is slower closer to the mass of the Earth.
Right, so imagine an apple hanging on a tree. The bottom of the apple is slightly closer to the center of the Earth than the top of the apple. Therefore, time is passing infinitesimally slower at the bottom of the apple than at the top.
The apple is aging at two different rates.
Yes. Now, one of the deepest principles in physics is the principle of maximal aging. Freely falling objects naturally follow the path through space-time that maximizes the time they experience. Because time is running at a gradient faster at the top, slower at the bottom, the straight line through four-dimensional space-time gets bent. The path of least resistance curves downward toward the slower time. The apple simply follows that curved geometry. It is not being pulled by a force. It is following the natural contours of stretched time and warped space.
That is breathtaking. It's not a lasso, it's just geometry. The path of the Earth around the sun is actually the straightest possible line it can take through a four-dimensional spacetime that has been severely warped by the mass of the sun.
The physicist John Archibald Wheeler gave us the most elegant, perfect summary of this complex dance. He summarized general relativity in one sentence. Matter tells spacetime how to curve, and spacetime tells matter how to move.
Matter tells spacetime how to curve, and spacetime tells matter how to move. The mass creates the dent, and the dent dictates the motion. But a claim this radical-like, rewriting the laws of gravity that had stood undisputed since Isaac Newton, required absolute, undeniable proof.
And Einstein provided it by solving mysteries that Newton's math was helpless to explain. The first great triumph of general relativity happened right in our own solar system with the planet Mercury.
Let's talk about Mercury's orbit.
For decades, astronomers had a problem with Mercury. Planets don't trace perfect circles, they trace ellipses, ovals, and that oval slowly rotates over time, tracing out a pattern like a spirograph toy.
Right, the orbit shifts.
Newton's laws of gravity were incredible. They could predict the orbits of almost everything perfectly. But when they calculated the tugs of all the other planets on Mercury, Newton's math was just slightly off. Mercury's orbit shifted by a tiny, frustrating extra amount that no one could explain.
The math was so stubbornly wrong that astronomers convinced themselves there had to be an invisible, undiscovered planet hiding between Mercury and the Sun, just tugging on it. They even named it Vulcan.
Exactly. But when Einstein finalized his equations in 1915, he applied his new geometry of spacetime to Mercury. Because Mercury is so close to the Sun, it is traveling through severely warped space and time. When Einstein ran the numbers through his new formulas, the calculation perfectly, flawlessly predicted that exact missing shift.
No invisible planet required.
No invisible planet, just curved spacetime.
He must have felt like he touched the face of God when that calculation balanced. But explaining an old mystery is one thing. To really prove a theory, you have to predict something entirely new. Which brings us to 1919, and the event that made Albert Einstein the most famous scientist on the planet.
The solar eclipse expedition. If general relativity was right, and massive objects literally create a dip in the fabric of spacetime, then even a beam of light, which has no mass at all, must be forced to bend and curve when it passes near a heavy object like the Sun.
But testing that is a nightmare, because you can't see the light of distant stars passing near the Sun. The Sun's glare is blinding, the sky is blue.
The only way to see stars right next to the Sun is during a total solar eclipse, when the Moon completely blocks the Sun's glare, turning day into night. In 1919, a British astronomer named Arthur Eddington mounted a grueling expedition to the island of Principe off the coast of Africa to photograph a total eclipse.
The stakes were astronomical, no pun intended.
They really were. Eddington took photographs of the star field right around the darkened edge of the Sun. Months later, he compared those photographs to pictures of the exact same stars taken at night when the Sun was nowhere near them.
And what did the comparison show?
The stars near the Sun appeared to have shifted from their true positions. Because the starlight had to travel through the warped, curved space surrounding the Sun, its path bent inward. From our perspective on Earth, looking back along that bent path, the stars looked like they had been pushed outward. The amount of bending perfectly matched Einstein's prediction.
This is what we now call gravitational lensing.
Yes, and today it is a fundamental tool in astronomy. We look deep into the universe and see giant clusters of galaxies with so much mass that they act as cosmic magnifying glasses. They violently distort, stretch, and bend the light of galaxies sitting far behind them.
Wow.
But in 1919, proving that starlight bends around our Sun was a revolution. When the results were announced, it made front-page news across the globe. Newton had been dethroned. Space was flexible.
Okay, so space bends, and we proved it with eclipses. But you also mentioned that time bends, that a clock near a massive object ticks slower. Have we proven that directly?
We absolutely have, and you don't even need to leave the planet to see it. Scientists have taken incredibly precise atomic clocks that lose less than a second over millions of years, and placed one at sea level and carried an identical clock to the top of a high mountain.
Because the peak of the mountain is further away from the dense center of the Earth's mass.
Exactly. The gravitational field is ever so slightly weaker at the peak, and just as Einstein predicted, the clock on the mountain runs measurably faster than the clock at sea level. If you live your entire life in a high-rise penthouse, your head literally ages a fraction of a nanosecond faster than your feet.
It is delightfully weird. And just a few years ago, we confirmed the final, most extreme prediction of Einstein's theory: the ripples in the pond.
Gravitational waves. Einstein's math showed that if you have incredibly massive objects accelerating violently, like two black holes orbiting each other at close to the speed of light, they should churn up the fabric of spacetime so intensely that they send physical ripples of distortion radiating outward through the universe at the speed of light.
Squeezing and stretching space itself as they pass.
Right. But Einstein thought we would never, ever be able to detect them, because by the time these ripples travel a billion light years to reach Earth, they are impossibly weak. They stretch and squeeze the Earth by an amount smaller than a fraction of the width of a single atomic nucleus.
But in 2015, we did it.
We did. We built the Laser Interferometer Gravitational Wave Observatory, or LIGO. These are massive L-shaped vacuum tubes, 4 kilometers long. We shoot lasers down these tubes, bounce them off mirrors, and recombine them.
Okay, so it's a giant version of the Michelson-Morley experiment.
Exactly. If a gravitational wave rolls through the Earth, it will physically stretch one of the 4-kilometer tubes slightly more than the other, changing the travel time of the laser by an unimaginably tiny fraction.
And in 2015, the lasers flickered.
2 black holes colliding over 1 billion light years away sent a shockwave through the fabric of reality. It passed through the Earth, squeezed our planet by less than the width of a proton, and our lasers caught it. A century after Einstein scribbled the prediction on a piece of paper, the universe rang like a bell and proved him right.
Okay, we have talked about exploding stars, colliding black holes, and the cosmic fabric of the universe. It is grand, staggering science. But I promised at the very beginning of this deep dive that all of this connects intimately to your daily, mundane reality.
And it does. Every single piece of relativity we've discussed today, time dilation from moving fast and gravitational time warping from curved spacetime, is locked in a daily battle over your ability to navigate the modern world.
Let's do the GPS reality check. Let's break down exactly what is happening in the phone you might be listening to right now.
The Global Positioning System is a network of about 30 satellites constantly orbiting the Earth. Each one of these satellites carries an incredibly precise atomic clock. When you open a map app, your phone acts as a receiver. It picks up a time-stamped radio signal from at least 4 of these satellites.
Okay, so it's just pinging them.
Yeah. By calculating exactly how long it took each signal to travel from space to your phone, it determines your exact distance from each satellite. Using geometry, it triangulates those distances to pinpoint exactly where you're standing on the surface of the planet.
But for that geometry to work, we are talking about insane levels of precision. We don't just want to know what city we are in, we want the blue dot to show us which lane of the highway we are in. Because the radio signals travel at the speed of light, an error of just 1 single microsecond, 1 millionth of a second in the satellite's clock, will throw your location off by 300 meters.
3 football fields of error for every millionth of a second. So the clocks on the satellites must be perfectly, flawlessly synchronized with the clocks down here on Earth.
And this is where Albert Einstein steps in to ruin the synchronization. Because these satellites are in a completely different physical environment than we are. They're dealing with 2 massive relativistic effects simultaneously, and those effects are actually fighting each other.
Let's look at the first effect, special relativity. The satellites are orbiting the Earth at roughly 14,000 kilometers per hour. That is incredibly fast compared to us sitting on the ground.
And as we learned with the train and the muons, speed causes time dilation. Moving clocks run slow.
Exactly. Because of their sheer orbital speed, the atomic clocks on the satellites tick slower than the clocks on Earth. They lose about 7 microseconds every single day just because they are moving fast.
Okay, so speed drags the clock backward by 7 microseconds, but then general relativity enters the arena.
Yes. The satellites are orbiting in space about 20,000 kilometers above the surface of the Earth. Up there, they are much further away from the center of Earth's mass. The gravity is weaker. The curvature of space-time is less severe.
And as we learned with the mountain peak, weaker gravity means time runs faster.
Precisely. Because they are experiencing weaker gravity, the clocks on the satellites speed up. They gain about 45 microseconds a day compared to clocks trapped down here in the heavy gravity at the surface.
So it's a cosmic tug of war. Special relativity is pulling the clock backward by 7 microseconds. General relativity is pushing the clock forward by 45 microseconds.
And general relativity wins the fight. If you combine those 2 effects, plus 45 minus 7, you get a net result. The atomic clocks on the GPS satellites drift forward by roughly 38 microseconds every single day.
38 millionths of a second. I can hear people listening to this saying, okay, that is fascinating trivia, but who cares? It's millionths of a second. How can that possibly matter to my commute?
It matters because of the unforgiving speed of light. The GPS signal is traveling at 300,000 kilometers a second. In 1 single microsecond, that signal covers 300 meters of distance.
Let me do the math. 38 microseconds of error multiplied by 300 meters.
It is roughly 11.4 kilometers. If the engineers who designed the GPS system had ignored Einstein, if they had treated time as a fixed universal background ticking away perfectly for everyone the way Isaac Newton thought it did, this system would accumulate over 11 kilometers of error every single day.
In 1 day, your phone would think you were on the other side of town. In 3 days, it would think you were in the next county. In a week, the multi-billion-dollar satellite network would be entirely useless. The planes couldn't navigate, the delivery drivers would be lost, the global supply chain would shatter.
To prevent this catastrophic failure, the engineers had to intentionally build the equations of special and general relativity directly into the software of the system. The computers are actively, constantly offsetting the time warp.
That is the ultimate realization of this deep dive. Every single time you order a rideshare, every time a package arrives at your front door, every time you map the fastest route to avoid traffic, you are actively relying on the physical bending of space and time. You are interacting with the curved geometry of the universe.
We tend to think of black holes and relativity as abstract science fiction concepts reserved for astrophysics, but they are foundational engineering principles required to run modern human civilization.
So as we wrap up, let's summarize the immense journey we've taken today. We started with a simple rule: the laws of physics are the same for everyone moving smoothly. Then we hit the brick wall of Maxwell and the Michelson-Morley experiment, which proved that the speed of light absolutely refuses to change no matter how fast you chase it.
Which birthed special relativity. To protect that universal speed limit of light, space, and time, we're forced to become totally flexible. Moving clocks genuinely tick slower, fast-moving objects physically compress, and the comforting idea of a shared universal now was deleted entirely.
And when Einstein realized he couldn't explain falling apples with that theory, he gave us general relativity. He showed us that gravity isn't a magical pulling force. It is the physical, topographical curvature of four-dimensional spacetime, warped by heavy objects, dictating the paths of planets, light beams, and falling keys.
Both theories utterly shatter our human intuition, and yet both are among the most rigorously, obsessively tested facts in the history of science.
Which leaves me with a final provocative thought that I want to offer to everyone listening. Think about what all this implies about your own brain. Our biology, our senses, our deeply ingrained common sense. They did not evolve to perceive the true nature of reality. We evolved merely to survive on the surface of one moderately sized rock. We evolved a brain that is excellent at calculating the arc of a thrown rock or outrunning a predator at a few miles an hour.
We are biologically calibrated for a very slow, very flat, very local world.
Right. Our intuition is incredibly narrow. So here is the question to ponder as you go about your day. If the fundamental fabric of reality is truly this bizarre, if time visibly stretches and physical space literally bends right in front of us, and we were completely blind to it until we managed to build highly sensitive interferometers and atomic clocks, what else are we entirely wrong about? What other basic fundamental common sense assumptions about life, consciousness, and the universe are completely backwards simply because we haven't yet built the right sensitive apparatus to see the truth?
It is a profoundly humbling thought. It reminds us that our daily human experience is just one tiny, distorted window into a universe that is far stranger and more beautiful than we can easily imagine.
It truly is. Thank you for taking this massive journey with us into the mechanics of reality. I hope the next time you drop an object or open a map on your phone, you feel a slight shiver of appreciation for the warped, flexible universe you live in. Keep questioning your reality, because as we saw today, the truth is entirely rooted in the unyielding dictatorship of light. We'll catch you on the next deep dive.